Hello everyone, so this is the second lecture in the frame of a course on adiabatic RF potentials for quantum gases given at the University of São Paulo in the context of the course of Vanderlei Bagnato. So I recall that the general outline of the course is a first lecture where I have given the tools about adiabatic potentials with radio frequency fields that you can check. And this second lecture will be devoted to giving you a gallery of possible traps and their applications that we can do with RF dress potentials. So I have told you that quantum gases present a high degree of control of their parameters, external and internal. And in this lecture, we will see that adiabatic potentials are still compatible with adjustment of the temperature, and they provide us, most of all, the dynamic control of the confinement geometry. They can give you access to periodic potentials or double wells, and also low-dimensional systems, 1D, 2D, are especially well suited for these traps. So the outline of this lecture will be as follows. I will give you the principle of adiabatic potentials, how we end up with the confinement frequencies, and then I will go through several examples of adiabatic potentials with various structures of magnetic traps that are behind. So first with the principles as proposed by Oliver Zobe and Barry Garraway already in 2001. Let me remind you what we have seen in the first lecture. We end up with the expression of the adiabatic potentials for dressed atoms in an inhomogeneous magnetic field B0 with a radio frequency omega. So in this expression, the detuning is the difference between radio frequency and local Larmor frequency. And omega plus is the coupling of the RF field with the spin, and more precisely, its projection onto the sigma plus polarization, where you have to keep in mind that sigma plus is defined with respect to the direction of the local static magnetic field. So there may be variations of the Rabi frequency due to the relative orientations of the static field and the RF field, even if the RF field itself is uniform. We have also seen that the trap minimum lies within the isomagnetic surface given by the detuning being 0. And this resonance surface is also given by the value of the magnetic field has some specific value proportional to the RF field. In the direction transverse to the surface, the confinement is strong, and we will see in a moment how to derive the expression of the oscillation frequency transverse to the surface. And right inside the surface, then the potential simplifies to just mh bar omega plus because delta is 0. So let us consider the really simplest case of inhomogeneous magnetic field, and this is just a linear magnetic field along some direction x. So B0 is just B prime times x. Then the Larmor frequency, which is GF mu B B over h bar, is just some coefficient alpha times x, and alpha is the gradient of magnetic field in units of gradient of frequency. The resonance surface, if we give some RF frequency omega, is set by Larmor frequency equals to omega. So if this is equal to omega, it means that x is equal to omega divided by alpha. So the surface, which is resonance, the isomagnetic surface, is just a plane, x equals to x0. The detuning, which is omega minus omega 0, I can also write in terms of this x0 as alpha times x0 minus x, such that the potential, if I take a uniform RF coupling, is given by this expression, some gradient x minus x0 squared plus omega squared. So these are the linear Zeeman state in the linear magnetic field, the RF coupling at some position x0, and the Dre states are given by this expression for m equals 1, 0, and minus 1. So now if we want to derive the oscillation frequency close to the bottom, how do we do? Well, we take this expression and we just expand it around x equals to x0. So of course the dominant term is omega plus, and then we write the second coefficient, the quadratic term, as some oscillation frequency squared times x minus x0 squared. So if we make the calculation, we find that the oscillation frequency that confines the atoms transversally to the plane is proportional to the magnetic field gradient. So the largest the gradient, the stronger the confinement, and inversely proportional to the square root of the coupling. So we could think that, okay, to have a very strong confinement to the surface, we can simply reduce the amplitude of the coupling. But this has a limit, because we have to remember that we need to follow the adiabatic theorem. And for the adiabatic theorem to apply, all changes in the state, which will be on the order of the oscillation frequency, must remain very slow as compared to omega plus itself. So this will set us a limit on the omega plus value we can get. We need to have omega plus large enough to avoid losses due to Landau-Zener transition. I will come to that in a moment. So another point I want to make here is that if we want to cool the atoms inside our adiabatic potential, we can just apply yet another RF field that we call an RF knife, which will be able to induce transitions between dress states. So this RF knife has a frequency which is a bit larger than the Rabi frequency and not the RF frequency. So if you apply an RF knife here, you will set the temperature to less than this value inside the adiabatic potential. So you can adjust temperature just as you do in magnetic traps. So let me come back to these Landau-Zener losses. If the RF coupling is not large enough, or if the gradient is strong enough and so strong that it increases the oscillation frequency very much, too much with respect to the RF coupling, then you will have losses in non-adiabatic states. So that means that you will allow non-adiabatic transition between dress states. And so here is a plot of the lifetime in the dress state as a function of the magnetic gradient. So the more you increase the magnetic gradient, the larger the oscillation frequency with respect to the RF frequency. And so the smaller the lifetime because you amplify the Landau-Zener losses. And this is another graph where we look at the temperature for different values of the RF coupling as a function of time. So for very strong RF coupling, there are no losses and we can hold the atoms very long. And there is a small heating in our experiments that explain the fact that the temperature increases a little bit. But now if we reduce the RF coupling omega plus, what will happen is that non-adiabatic transitions will occur, Landau-Zener losses. And in fact, they occur more for atoms that move fast, because if the atoms move fast, they are less adiabatic. So we remove atoms that move fast more than the slow atoms, and this leads to cooling. So if you look for smaller amplitude of the RF field, where there are Landau-Zener losses, the total lifetime is less and the temperature decreases. It's a kind of evaporation induced by Landau-Zener losses. So I will close this point on Landau-Zener losses, and from now on consider that we don't have these losses and stay in the adiabatic potentials. So let's look at the structure inside the isomagnetic surface where the atoms are. So if the detuning is 0, we just have omega plus for the potential. So if I consider isomagnetic surfaces, as in this case for a planar quadrupole trap, setting the RF frequency to some value will choose a given resonance surface where the atoms will sit. So the more red is the graph, and the more atoms there are. So this corresponds to the minimum of the potential. If I choose another value for the RF field, of course, it will change the isomagnetic surface the atoms are confined to. So it will change the radius of the surface to which they are confined. If the omega plus parameter is uniform and we are in the presence of gravity, gravity will act and gather the atoms at the bottom of this surface. But if, on the other hand, the major element is the variation of the RF coupling, then the atoms will gather at the points where the RF coupling is minimum. And this is a way where double waves can be produced, as we will see in a moment. So let me now start my second part and give you nice examples of what can be done with adiabatic potentials. So I will start by considering underlying magnetic field given by a Joffé-Pritchard trap. So let me just remind what it is. 4 bars with alternate values of current plus 2 coils with current in the same direction, which gives rise to this expression for the magnetic field. So transverse quadrupole plus curvature. So the isomagnetic surface in this case are kind of elongated ellipsoids, and in the center the magnetic field is non-zero and aligned along X. So depending on the global RF polarization that we choose, we will have a different behavior for the local coupling omega plus inside the resonance surface. If I choose the RF polarization sigma plus along the x-axis, it means that it will couple maximally along this axis, but a bit less on the sides, then omega plus will be smaller on the side with respect to the two ends. So the minimum will be around the center here, giving rise to something like an annular trap. On the other hand, if I choose a polarization which is linear along y, so y being this transverse direction, so that's the direction where the coupling will be smaller, and the atoms will accumulate at 2 opposite points of my ellipsoid. So this is the first example I would give, because it was the first realization experimentally of RF-just adiabatic potential, a bubble trap in the presence of gravity. So in this experiment, gravity is more important than these effects of variation of omega plus on the surface, so we can neglect them. And we simply have to imagine that the atoms will gather on the isomagnetic surface defined by the value of the RF frequency, which depends if omega 1 is small or larger, you will have a small or a large bubble. So this experiment was done in my group at the early years 2000. In this case, we can even create an ultra-cold atomic bubble on Earth if the temperature is large enough, because if the temperature allows you to reach the other point on the top of this bubble, then you can populate everywhere the bubble and get this kind of nice bubble on Earth. So this picture is taken from the thesis of Olivier Morisot. Now, the second example I would like to show you is how to make a double well. So in this case, you use inhomogeneous RF coupling with a linear polarization transverse to the isomagnetic surface. And here the situation was such that the size are very, very small, so gravity is not playing a major role. Instead, the structure with omega plus on the surface plays a major role. So what we expect is that by varying the RF frequency, we get 2 different wells that are split more and more when RF frequency is increased, and that's what was observed in the group of Jörg Schmidt-Meyer in 2005 in this paper, where you make the image of atoms along the long direction and see that the splitting depends on the RF frequency. So starting from these double traps that can have tunneling between them, you can get some interference fringes after releasing the 2 clouds. So you switch off the trap, you let the 2 gases expand in free fall, and so each cloud is expanding, so they overlap the 2 clouds, and they give fringes with a separation which is larger when the clouds are closer to each other. So this technique has been used to study the coherence of one-dimensional gases and the way that the phase derives after a sudden splitting from one single gas to two gases. So initially they just have one gases, then they split with the RF, and initially as the two gases have the same phase, you have interference fringes that are more or less straight. But when you wait more and more, each gas has its own phase that evolves, and the interference fringes start to have big wiggles, and this way you can study how the coherence is lost when time goes by. I would also like to mention that using these atom chips, as was used in the previous experiment, you see that it starts with a chip, it has been possible to realize also a ring trap using this time a circular polarization along X, as I was mentioning. Then the atoms accumulate all around, and this picture has been taken by the group of Dana Anderson. So now let me go to another situation where we start from a quadruple trap and introduce dressing. So the quadruple trap is the situation where the magnetic field is 0 at the center and increases linearly with position. So there was a problem in a quadruple trap to have the atoms close to the 0, but if you maintain now the atoms on an isomagnetic surface, which is an ellipse far away from the 0 of magnetic field, of course, you don't have this problem anymore. So there is no problem of spin flip at the center because the atoms are not going to the center. Locally, around this ellipsoid, which has a factor of 2 in the vertical direction with respect to the horizontal, depending on the global RF polarization, either you have a minimum of coupling at the top if the polarization is circular with respect to the vertical axis, or you have two minima at the sides if you choose a polarization which is linear along that direction. So what is special with the case of the quadruple trap is that any direction you choose for the polarization, you will always have points where the coupling vanishes, so where you would have the two the different adiabatic states that touch each other, and you will have adiabaticity which is lost. So in this case it is at the top. In this case there are 2 points where atoms can escape because the coupling is 0. So now if we start with the circular polarization and we take into account gravity, what will happen is that the atoms will gather at the bottom of this ellipsoid. So in this way, you can create very anisotropic two-dimensional potentials, because the transverse confinement, which scales as gradient divided by square root of omega plus, can be rather large, like kilohertz, whereas the horizontal frequencies are the ones of a pendulum on the order of tens of hertz. So you can have a large anisotropy between vertical and horizontal directions. You can also adjust in the plane possible anisotropies between x and y by using a different polarization from, for example, circular, where it is symmetrically equal with respect to linear, where you have a direction where the frequency is less. And this geometry you can modify dynamically with time. So this makes this situation ideal for the study of collective modes of the two-dimensional gases, and this is what we have done in my group, where we have excited the gas at the bottom and looked for the eigenmodes of the gas. So here 3 modes are represented, the center of mass mode in the x and y direction, and this one is the scissors mode, where the gas evolves with tilt around a main axis. So in this trap, we can also study fast rotations of 2D gases and create vortex lattices, as is in this example. Now, using this underlying bubble, we can also access rings if we add light fields in addition to the RF field. So in this example, using 2 laser sheets blue detuned with respect to the atomic transitions, provide you with a confinement in between the 2 sheets. So you load this trap as follows. So you start from the ellipse as before with the atoms at the bottom, then you switch on the laser, and then you shift the bubble by adding a vertical magnetic field that will simply shift the quadrupole. up to the point where the atoms are at the equator. So this has been proposed in my group in 2006 and realized first in the group of Chris Foote in Oxford and then in our group. And with the tuning parameter that we have in the bubble, for example, changing the radius by changing the frequency, of course, we can change the radius of the ring in the same way. So in this kind of rings, you can access all the physics that is related, that is called atomtronics, where essentially you replace electrons by atoms in microcircuits. And so this is an example of things you can observe with rings. You can create persistent currents in the ring as you create them for superconductors with electrons in solids. And if you set the gas into rotation, then there will be a signature in the time-of-flight expansion. So without rotation, a ring in time of flight will have a peak in its distribution, whereas when you induce rotation in the ring, then there will be a hole in the center after expansion, and the size of the hole gives you an indication of the circulation of the velocity all around the ring. So in this example, persistent currents were observed up to a couple of seconds. So now let me come to another possible application using multiple RF fields. So not just one RF frequency, but several RF frequencies. So if you have several RF frequencies, then you can have a first avoided crossing at a first frequency, and then another avoided crossing at another frequency, and yet another one. So in this way, you see that you may have several wells each time you have an avoided crossing. So this was proposed by Courtey and co-workers in 2006 to realize lattices in this way. So it's more bubble inside other bubbles. And it has been used in the group of Chris Foote to create two-dimensional gases on top of each other with a population in the two gases that you can tune by tuning finely the amplitudes of the RF fields. You can even make these traps sensitive to the internal state. So in this example, you have together trapped the F equals to 1 and F equals to 2 hyperfine state of rubidium. And it may be a single trap for one species, whereas it is a double trap for the other species. And if you change a parameter, you can make just the other way around, a double trap for F equals 1 and a single trap for F equals 2. So you can make spin-selective potentials using these RF fields. So if we go back to just a single spin state, but two different wells, this situation has been used in the group of Chris Foote to study the quench from the superfluid state to a normal state in a two-dimensional gas. So they start with a superfluid in a single 2D trap, and then they split the gas into two using these three RF frequencies. As there are only half the atom number in each of the clouds, this goes from the superfluid state to the thermal state. There are not enough atoms to be superfluid. And then they follow the evolution of the interference pattern between these two clouds as time goes by after the quench. So initially, the fringes are very straight, there is no phase defects, and then when time is increased, you see that there are wiggles in the interference pattern, and at some point you even see some defects appearing. This is the signature of a vortex, for example. So this has just been released on arXiv in 2002. And another trick you can apply is to make the RF field time-dependent, or the magnetic field time-dependent. So if you start with the dress quadruple trap, so this bubble with the atoms at the bottom, and now you imagine that you modulate the static magnetic field in the vertical direction. So if you add a homogeneous magnetic field, you just shift the bubble. But now if you do it very fast, you see that it will excite strongly the atoms that are at the bottom. On the other hand, the atoms that are at the equator are tangent with respect to the potential, so are much less excited. So by doing that, you are able to produce a ring trap which is very smooth because there is no light field at all. So of course you have to follow a given order for the frequencies. So the oscillation frequency should be much less than the modulation frequency, which must be much less than the RF coupling to ensure adiabaticity, which is itself must be less than the RF frequency. So this has been proposed by Igor Lezelewski and Wolfgang Klitzing, and first realized by the group of Chris Foote. Here you see an example with two different radii. And it is used in the group of Wolfgang Klitzing for atom interferometry. So the idea is to prepare a cloud and to accelerate it all around the ring to see how much you can keep it in the ring without excitation. And so Wolfgang Klitzing has demonstrated that these time average adiabatic potentials are extremely smooth because they can accelerate the atoms during about 14 seconds with very, very small heating. And this is what you obtain when atoms are moving very fast inside this guide. So this will be used for atom interferometry and measuring rotations in ring. So finally, the last point I would like to make is that we would like also to access the whole surface, so bubbles. Why would that be interesting? Well, because the bubble has a different topology than a flat trap or a ring. For example, on a bubble, if you have vortices, they should come by pair. If you have one plus vortex here, there must be a minus vortex somewhere else. Also, these bubbles have specific collective modes that you cannot find in other type of geometries. But of course, to have the atoms filling the bubbles everywhere, you need to cancel gravity. And so a project has been embarked on the International Space Station just for this purpose, to work in a microgravity environment and try to fill completely the adiabatic surface of a Joffrey-Pritchard trap to get a bubble. But maybe we can do that also on Earth. And that was our aim in a collaboration with Vanderlei Bagnato, to compensate for gravity in this situation of the Dress quadruple trap. And so the idea is that gravity is pushing the atoms downwards, but if we use a sigma plus polarization for the RF pushes the atoms upwards towards the region where the magnetic field is 0. So maybe this can be used to fight gravity. The dependence of the RF amplitude is also linear with the position, just as gravity is. So if we choose the good value for the radio frequency amplitude for compensating gravity with the gradient of RF amplitude, then we should end up with a gas where the potential is everywhere the same all around the bubble and compensate for gravity. So we tried that. And as soon as we increase the magnetic gradient, which is the same as increasing the RF coupling, we see that the atoms climb more and more on the side of the bubble and fill the bubble more and more, up to the point where we expect to compensate for gravity. But there, instead of filling the bubble everywhere, we find that the atoms accumulate at the equator of the bubble and do not reach the top. And so why is it that? In fact, we should take into account the transverse trapping frequency, remember the one which is proportional to the gradient divided by square root of the RF coupling. And this transverse frequency decreases from the bottom of the bubble to the equator and then increases again from the equator to the top. It is minimum near the equator. And in fact, this transverse frequency is the one which is responsible for the confinement at the equator. Indeed, the potential on the shell is just omega plus, which we have decided to use to cancel for gravity, so this is 0. But we also have to add the 0-point energy of the transverse confinement. And this 0-point energy for the transverse confinement is the one that will be responsible for accumulating the atoms towards the equator. So it's not so easy to realize bubbles on Earth or in the International Space Station, because this effect is also true in the International Space Station. So the theory predicts that the atom will accumulate to the two ends of the Dirac-Joffé-Pritchard trap, and that's also what is seen in the experiment in the International Space Station. So anyway, these pictures are for thermal gas, not a BEC, but it is a difficulty to be able to fill a bubble. So let me summarize. I have presented you several applications of adiabatic RF potentials, double wells, two-dimensional gases, ring traps, and in fact you can do even more complicated geometry if you consider using chips over which you deposit wires to create both the magnetic trap, the RF trap. You can imagine to have some specific guides for your atoms. So I finish by giving you again the two references that you can consult if you want to know more on RF-driven adiabatic potentials. So this one is giving you a detailed theory of this phenomenon, and this one is giving you recent applications of RF-driven adiabatic potentials, including these double wells or microcircuits. Thanks for your attention.